technique of integration. Integration by substitution using trig functions, or as I'm often going to call it, trig sub. So there are integrals where we can make a substitution, where we make a substitution where u equals some trig function. So this is a little more, this is a little trickier than what we've done in the past. But this is for a very specific kind of problem. For example, this one. The integral of the square root of 9 minus x squared over x squared dx. Now, the problem in this integral, what's an obstacle for us, is the fact that we have the square root of something. And that generally makes a chunk of something that we can't manipulate. So what turns out is that we can make a substitution which turns that into the square root of something that we can actually take the square root of. And that's what's nice about this technique. So we make the substitution x equals 3 sine t. And then that would make dx 3 cosine t dt. So first of all, let's see why this works. So after you make that substitution, first of all, naturally just plug it in. And then work it out. So what happens in the top? Well, you've got 9 minus 9t squared. So we've done some simplifying algebra there. What you can do on top is factor out that 9. And factoring out the 9 under square root, we can just pull that out as a radical 9, which is 3. First of all. Second of all, what's left under the radical? 1 minus sine t squared. But 1 minus sine t squared is just cosine squared. Exactly. And the square root of cosine squared, naturally, is just cosine. So making that substitution gave us something we could take the square root of, and the radical goes away, and we now have things that we can actually work with. So now we're just in a situation where we have to do the integral of, and of course we're also manipulating it, doing the algebra, simplifying the constants, etc. So now we just have the integral of something that is powers of trig functions, and this we know how to work with. This one actually works out very easily, because cosine over sine is just cotan squared. And for dealing with cotan squared, we actually have a trick. Replace it with cosecant squared t minus 1. Remember that for cotan squared, the trick is similar as the trick for tan squared. And the integral of cosecant squared t is just negative cotan t, and then minus t plus c. But we're not done, because this expression is in terms of what variable? This is in terms of t. But what should it be in terms of? It should be in terms of x. So we must convert back to an expression in x. But how do we replace t?
Instead of t you put x, that's 3 sine t.
Right. So what we know is that x equals 3 sine t. Okay. So from that, we know that x over 3 equals sine t. And so therefore, just using arc sine of x over 3 equals t. So we know how to replace just t. But what about cotan of t? So for this, we're going to have to use our knowledge of trig. And we're going to make the trig triangle. So what's the trig triangle? It looks like this. So first of all, where does t go in this picture? T is the angle. Right? We're taking sine of t, cotan of t, so t represents the angle in our picture. So I'm going to label the angle t. Okay. Now, what do we know about this? We know that, based on our substitution, x over 3 equals sine of t. Well, what's the definition of sine? Opposite over hypotenuse. So that means that opposite over hypotenuse is x over 3. And now what can you do? You can solve for the third side. So x squared plus adjacent squared has to be 3 squared. So you solve that out, and you get that it has to be the square root of 9 minus x squared. So now we know the 3 sides, so now we can say whatever trig function we want. In this case, we want cotan t. So what is cotan t?
It's hypotenuse over
A over
H
over
over
3. It's opposite over
opposite.
It's well. What is tan? What is tan t?
Adjacent over
Tan t is opposite over adjacent. Cotan t is adjacent over opposite. So there's cotan t. So we had to replace cotan t. We had to replace t. We now know what both of those are. So now we have our final answer.
Don't we have to repeat? Oh, because it's plus c. Okay, no.
So how do we know what to substitute? Well, the substitution of sine t worked because the square root of 1 minus sine squared t equals cos t. So when you have something that looks like 1 minus x squared, the square root of 1 minus x squared, then we're going to want to use a sine function. But in addition, what else do we have to keep track of? We also need to properly choose the constant so that it would factor out. So in this case, this looks like the square root of 1 minus x squared, so we know we're going to want a sine, but there's a 9 in front, so what does the constant have to be?
3.
The constant has to be 3. So the substitution winds up being 3 sine t.
Could you use 3 cosine t instead as well?
Drop the negative. Okay. Okay, so does that, so sorry, I just put the negative in there. Yeah?
In this problem, could you pick 3 cosine?
Yes.
Squared.
Yes. So I'll make just the quick comment that you're right, because the identity is cosine squared plus sine squared equals 1, then I use sine and we'll typically use sine, but you could use cosine if you wanted. Yeah. Okay. And then, so as a final note to this problem, the radical from the original integral will often reappear in the answer. And that's just like a side note. It'll just happen naturally. You don't need to worry about it. Okay. So this was the trick where we used the identity cos squared t plus sine squared t equals 1. Guess what? We're going to apply this trick to a similar trick to other integrals as well. So the integral of dx over the square root of 16 plus x squared. What trig identity does this look like? What substitution should we use?
1 plus tangent.
Yeah, so this looks like tangent. What's the tangent identity?
1 plus tangent squared equals cotangent squared.
1 plus tan squared x equals secant squared x. So based on that, which one's going to be our u?
4 tan x.
Yeah, you got, that's great. U equals 4 tan t, exactly. Because we want the tan to be in there, or another we want tan squared to be in there, so then we're going to wind up converting it to secant and taking the square root, is the idea. Okay. So x equals 4 tan t. So dx will be 4 secant squared t dt. So when you make that substitution, you get this. And now I'm missing a parenthesis. Okay. And now you just have to do arithmetic and algebra. So you square it and this happens. Now what do you need to do in the bottom? That's a key step.
Take
factor out that 16. Exactly. So you factor out that 16, and you get your 1 plus tan squared, which is perfect. That's what we want. So the square root of 16 becomes 4, and then 1 plus tan squared becomes secant squared. You take the square root of that, and you just get secant t. So now this simplifies, and all you just have is the integral of secant t dt. And we've done this integral before. So I'm not going to go through those steps again, but this works out to that. ln of secant t plus tan t, and then stick a plus c at the end. Okay, but once again, we're not done. Why are we not done? Got to put it back in terms of x. So in order to do that, we need the trig triangle. So here's the trig triangle. So what do we know? We know that, oh yeah, so what do we know? Sorry, before I give you the trig triangle, what is it that we know that we're going to put on the trig triangle?
Tan t equals 4, x over 4.
Tan t equals x over 4. And those are the things that we know. So when we set up our triangle, we've got x over 4 is tan t. And then you can fill in the third side. So it'll just be the square root of x squared plus 4 squared. So now, so let's see. So what do we need in our answer? We need tan t. Well, we already knew that was x over 4. We also need secant t. So what's secant t? 1 over cosine. Okay, so what's that? In this triangle, what is that?
Hypotenuse over adjacent.
It's hypotenuse over adjacent. Exactly. So notice that you're going to need to remember the definition of your 6 trig functions in order to do these problems. Okay. So right. So therefore, secant t is just this. And so then we can write the final answer. It's ln of square root of 16 plus x squared over 4 plus x over 4. And then plus c. Okay. So once again, the substitution of tan t worked because we had a radical of constant plus something squared. And so when that becomes tan, it works out then just the square root of secant squared, which is just secant t. So notice that we can do any integral that looks in this kind of form using trig subs. Let me also point out that we can actually use this technique to prove some formulas that we've seen before. Okay. The integral of 1 over 9 plus x squared dx. Well, this almost looks like which integral that we know what it is. This almost looks like arctan, but what's slightly different?
9.
There's a 9 there instead of a 1. If it was just a 1, it would just be arctan x, we'd be done. But there's a 9 there, so what do we do with that 9? Okay, it's not a factor, so you can't factor it out.
The square root or something?
Something, okay? So if you've memorized the formula, you know what to do with the constant. But if you haven't memorized the formula, we can just go after this and treat this like an integral that we're going to do using trig sub.
You can use them for the square root or something?
We're going to trig sub because even though there's no radical, we can just do a trig sub. So what should x be replaced by?
310.
It should be 3 tan t. Because we're going to use the identity that 1 plus tan squared equals secant squared. So when you put that in, you get the integral of 1 over 9 plus 9 tan squared t times now 3 secant squared t dt. And now we have to work this out. So in the bottom, you factor out that 9, because now 9 is a factor in the bottom. And you do some canceling, and you get this. So I should say the 3 in the top and the 9 in the bottom cancel out, and that just gives you 1/3. And then you've got secant squared t on top and secant squared t on bottom. So what do you get? Just get 1. And the integral of 1 is just t. So this winds up being 1/3 t plus c. But of course, we're not done. We've got to put it back in terms of x. So the question is, how do we do that? In this case, you don't even need. You don't even need your trig triangle. You can simply say that since x was 3 tan t, then x over 3 is tan t. Therefore, arctan of x over 3 is t. And because the integral worked out so simply, that's all we need. So the answer is 1/3 arctan x over 3 plus c. And look at the original integral. Now you can see what to do with that constant. So it's easier to remember if you think of it in the following way. Think of 9 as 3 squared. If you think of it as 3 squared, then this works out very nicely. It's just 1 over 3 arctan x over 3. So for example, if you had the integral of 1 over 25 plus x squared dx, what would the answer be?
1 to the 5, 1 over 5, tan x over 5.
Exactly. 1 over 5 arctan of x over 5 plus c. And so that is a general formula. And you can similarly prove, so what other integrals? We've also used a lot the integral of 1 over the square root of 1 minus x squared dx, and that one was arcsine. And you can similarly prove what that one should be if it's not square root of 1 minus x squared, but it's, say, the square root of 16 minus x squared. And those formulas, you can just either prove them yourselves or just look them up in the book. But I just wanted to show you that you can use trig sub in order to actually derive what those formulas are. So far we've used 2 trig identities, but there's one more. And we can see another type of integral that will let us solve. So the integral of the square root of x squared minus 1 over x dx. Which identity does that look like? Or what can we replace? So it's exactly that. So in this case, we're actually using the same, we can actually use the same identity, but we're rewriting it so that we have secant squared minus 1 is going to equal tan squared. So once we do, so that's the substitution. And notice that in this case, the constant is 1, so there's nothing to worry about as far as that goes. So x equals secant t, and then from that dx equals secant t tan t dt. And replace. So you substitute, you get this. And now we just need to do some, a little bit of trig replacement and then some algebra. So, so I just canceled the secant, so no more fraction. And this winds up being the integral of tan squared t dt. And this, again, is something that we know how to do. This is the easy one. This is a nice little trick. That's just secant squared t minus 1. And we know how to integrate that. It's just tan t minus 1. Excuse me, tan t minus t. And once again, we have to, right. we have to convert back to x. So for that, we need the trig triangle. So your angle is t. And what do we know? We know that x equals secant t. So how do we put that on the triangle?
Secant is 1 over sine, right?
Secant 1 over cosine.
1 over cosine.
Right.
So it's
Hypotenuse is 1.
hypotenuse over adjacent.
Right. So this is
So x is hypotenuse.
hypotenuse over adjacent. So x is the hypotenuse, then what's the adjacent?
Yeah, adjacent is 1.
Adjacent is just 1. So think of x as just x over 1. So x over 1. So secant of t is now x over 1, which is just x. And now, of course, you can find the other side as well. Square root of x squared minus 1. And no surprise, that's the radical that we started with in the original problem. So now, we just rewrite the answer. Oh, okay. So right. So what is? So what's tan t? Tan t, opposite over adjacent. Square root of x squared minus 1 over 1. So we don't need that part. And then finally, what's t? Right. So t is just arcsecant of x if you go back to our original substitution. Oh. Right. So now arcsecant, maybe you don't like arcsecant. That's fine, you don't have to use it. We've got a triangle here, you can define t any way that you like. You want to use arc cosine, you want to use arc sine, fine. Pick whichever one you like. You got options.
Wouldn't it be nice to have x at 1 and not that radical?
And of course, plus c. Okay.
What? Adjacent over hypotenuse or cosine?
It should be
Is it cosine?
cosine x. Adjacent.
Hypotenuse over adjacent.
So
Oh.
cosine is x.
Sorry, I got that. Right, so sorry. Cosine t is 1 over x. So this should be like that, sorry. Other way around. Thank you. Okay. And then once again, in this case, we used secant t because the square root of secant squared t minus 1 is just tan t. That's why we use that substitution for this problem. Okay. So those were the basic trig substitution problems. We saw, so those are the 3 types, where you can substitute using a sine function, substitute using a tan function, or substitute using a secant function. And as someone mentioned before, you can also use the identities in different ways. Instead of sine, you can use cosine, et cetera, et cetera. But typically these are the 3 ways that we think about because we want to simplify our possibilities. And these work. Okay. So next, we're going to look at the harder types of trig sub. Slightly harder. So, about this integral. So why is this a candidate for trig sub? And which one would we use?
Something over square plus 1.
Right.
Square root.
So we have an x squared plus 1, so that tells us which trig sub would we think about using? We think about using tan. That's the first thing. Second thing is, why is this a candidate for trig sub?
Because it has a
Yeah. What's that exponent?
left radical.
The exponent is 3/2. So if it's 3/2, what is that implicitly telling you? There's actually a square root in there. This is, if you like, a square root raised to a third power. So there is still a square root in there, so we know that we can get rid of that square root using our trig sub techniques. Okay. So that's what we're going to do. So in this case, the constant is 1, so we use x equals tan t. And then dx equals secant squared t dt. And now we just plug in and see how it simplifies. So you get this. And now we can simplify tan squared t plus 1. You know, that should be secant squared t. Now secant squared t to the 3/2 is just secant to the third. So what do we get? 1 over secant, which is just cosine. That's the easiest integral we can get.
Why is secant? What's sine?
So get sine t plus c. But we're not done. Because
To get X.
we've got to get it back in terms of x. Okay. Now we just got to do a little trig. So we use our trig triangle. So the angle is t, and what do we know? What do we know about t and x?
X is the opposite.
Right. So we know that x equals tan t. So tan t is by definition what? Opposite over adjacent. So the opposite side is what? X, and the adjacent side is 1. Which makes the hypotenuse the square root of x squared plus 1. And we must have done something right because that's the radical from the original integral.
Because I got the variable mu.
Ooh. Okay, so we need to know what's sine t. So what is sine t?
Sine t is x over radical x squared plus 1.
Exactly. So it's that plus c, and that's the answer.
If we had sine t plus t.
So in this, so when you have a rational exponent, you do have a rational exponent with a 2 in the denominator. You do have a radical. It's just hidden. As you do have a square root, it's just hidden. So you have to be aware for that. Okay.
Isn't that like always true? Can't you say 2 over 2 or something?
Not interesting. Yeah. Okay. In that case, you don't need it. Okay. Next. Trig sub, completing the square. So, yes, for completing a square, you're going to need to use some algebra. Okay. So what if you're supposed to calculate the integral of dx over the square root of x squared plus 10x plus 26?
Factor inside first.
Yep. So look at the denominator. So you can nicely split that 26 up into just a 25 plus 1. And now what does that let you do? X squared plus 10x plus 25. That lets you rewrite the integral in this way. And now that you've done that, what can you do? Now we can do, let's see. You can do a trig sub directly if you're very clever. I'm not that clever, so I just did a u sub first. So I said let u equal x plus 5, so du is just dx. And now that gives us this integral. And now how do you do this integral?
Another substitution.
What substitution would you use?
Anything you want. Just name it.
Tan squared plus 1 equals.
Right,
whatever
but yes, so u equals what?
U equal 10.
U is just going to be tan t.
10
And then this will be
Right.
secant.
And then you just, right, du equals secant squared t dt, and then you just work out the rest of the integral. Okay. So this is the basic idea. Does that make sense? Okay. So the extra trick here is to recognize that under the radical, you have a quadratic expression. And what we can always do with a quadratic expression is complete the square and then substitute. So we have u squared plus 1, or 1 minus u squared, or something like that. And then we can use our trig sub. So there's an extra algebra layer in the first step. Okay. Here's a more general and one that you have to think about. Okay. So this is a candidate for trig sub. Why? Because there's a square root and there's an x squared under there. But it's not presented in a nice way. So it requires some algebra to put it in the proper form. So first we have to complete the square. So how do you complete the square? So the first thing is you want your constant in one place, and then you want your x terms there as well. And you always want the x squared term to be positive. So that's why we put it in those parentheses. And now how do we complete the square on x squared plus 2x? What's missing? What's missing is a 1. So we stick a plus 1 inside the parentheses. Putting a plus 1 inside the parentheses, since there's a minus in front, is really like subtracting 1. So to make up for that, you have to put a plus 1 on the outside. So now we've completed the square because that is just x plus 1 squared. And then also collect the constant terms on the outside, that just gives you 4. So do a substitution. U equals x plus 1, and then you see that what you have, okay. Let's see. Right. So we need to replace, so x plus 1 becomes u. Then we also need to replace the x on top. But that we can do because this is such a simple u sub. U equals x plus 1, well x is just u minus 1. So you replace that on top, and then dx is replaced by du. So now we have this integral. Now how do you do this integral?
Sign substitution.
Okay. So it is going to be a sign substitution.
King sign.
Let's see. You could split it. It turns out you can either split it or not split it. Both of them will work. So in this case, we're just going to dive straight into the substitution. And right, it's a square root of 4 minus u squared, which looks like 1 minus x squared, which is just a sign substitution. And in this case, 4 there is like 2 squared, so we need a 2 in front. So you get u equals 2 sine t. And then naturally du is 2 cos t dt. Now we make all those substitutions. Now I have to do some algebra. So on the bottom, factor out until you get 1 minus sine squared. It's just going to be square root of cos squared. That just gives you cos, and the square root of 4 becomes 2. Oh, and some things cancel really nicely. So just get the integral of 2 sine t minus 1. Negative 2 cos t minus t plus c. But we're not done. Because we got to put it back in terms of x. So, what do we know? So, what do we actually have to put it back in terms of first? In terms of u, because we made 2 substitutions in this problem. Okay. So we got to unwind it. So, what does our triangle tell us? What was the substitution that we made?
Sine equals 2 sine t.
U equals 2 sine t. Therefore, what sides do we know here?
Sine t would be equal to u over 2.
Right.
So it would be, opposite over hypotenuse. So it would be u, the opposite hypotenuse would be 2.
There you go. And therefore, that final side would be the square root of 4 minus u squared. And we must have done something right, because that brings us back to the radical that we had in the u integral that we were doing. Okay. So now we have our triangle, but what are we trying to replace?
The t.
So first we're trying to replace cosine t. So what's cosine t? Right. Square root of 4 minus u squared over 2. So that's cosine t. Now we also have to replace t. What's t?
T is arc sine of sine.
Right.
I mean,
So
arc
sine t is u over 2. So t is just arc sine of u over 2. So we put it back in u, but we still have to get back and write it in terms of x. Well, that was easy because u equals x plus 1. So you can replace the u with x plus 1, replace the u with x plus 1, and you get the first thing. Now, if you want to be slightly clever, you can realize that the 4 minus x plus 1 squared is actually just the very same thing that we started with in our original integral. So if you like to come full circle, you can write it as we had it in the original integral. But like I said, so writing it either way is fine. So that was kind of a tricky one. It required a couple techniques of completing the square, 2 different substitutions. So this is a little bit on the hard side, but something that you have the skills to do. So those are all the different, those are some of the different ways that you can use trig sub. First the basic ones, then also rational exponent, then also completing the square. Let's sum up. Trig sub. So what's the indicator for trig sub? The indicator is, first of all, you have some kind of square root, and second of all, you've got a quadratic expression inside. So what do you do when you see those things to do trig sub? First of all, if necessary, complete the square and do a substitution. That's the first thing. And then once you have something that looks like it's ready for a trig sub, here's what you do. When you have each of these different forms of square roots, that's the substitution you can make. So the square root of a squared minus x squared, substitute x equals a sine t. And we're going to use that identity. If you have the square root of a squared plus x squared, that looks like this identity, so you're going to use x equals a tan t. And then finally, if you use the square root of x squared minus a squared, that looks like you should use secant there, so x equals a secant t. And two notes from when we did the problems. This also applies when we have rational exponents with a 2 in the denominator, because rational exponent with a 2 in the denominator basically means you've got a square root. And of course, we also need to do the undo the substitution. And almost always, to undo the substitution, we're going to need to use a trig triangle. Not always, but almost always. So I want to now use this technique to solve an old problem that we've encountered before, and we solved it with a real trick. But we were only able to solve it in special circumstances. So you guys remember this integral, the integral of the square root of 9 minus x squared dx. How did we solve this before? Before we said, oh, that's just the equation of a circle. And it's a circle with what radius? A circle with the radius 3. So for example, you'd be given this integral and told to do it, say, from -3 to 3. Or do the integral from 0 to 3. And you'd say, oh, I don't have to do the integral, I just know that that's the area under a circle, either 1/4 or 2/4. And you just wash your hands of the problem right there. But what if the boundaries are something different? Or what if there are no boundaries at all? What are we going to do? Well, now look at this integral. How can we do this integral? We can do it with trig sub. And we're going to use x equals 3 sine t. Exactly. So dx is 3 cos t dt, and we get to work. So plug it in and do some manipulation. Factor out that 9. Square root of 9 will become 3. 1 minus sine squared becomes cosine squared, and the square root of that is just cosine. So now we can simplify this a little bit. That 3 times 3 becomes a 9 in front. So now we've got 9 the integral of cos squared t dt. That's as far as we can go with this trick. How do you do the integral of cos squared t dt? So this was the annoying one, because to do integrals of powers of sine and cosine works best when you have an odd power, and you just put one on the side. But that's not this one. This one is when you have only even powers. When you have only even powers, you have to use the double angle formula. So you have to rewrite this as 1/2 of 1 plus cos 2t. And now we're going to integrate it. So I'm going to take that 1/2 and I'm going to pull that outside. And the integral of 1 is then just going to be t. And the integral of cos 2t, well, the integral of cosine is sine. But remember, you have to track that constant, that 2 in front of the t. So if you do a u sub really quickly, you can see that that's going to just pop out as a 1/2. So I included that as the 0.5. But are we done?
No, we have to sub the t.
Got to put it back in terms of x. So we need to replace t. So what do we know about t?
As T is arc sine.
Right. So x equals 3 sine t. So arc sine x over 3 equals t. So we can replace t. That's not a problem. But now the problem. We know how to handle trig functions of t, but what do we do with sine of 2t? Our substitution only lets us make a trig triangle with the angle of t. So what do we do with sine of 2t?
Divide by multiply.
You can't just pull out the 2 and say everything's fine. So here you have to use some more clever trig identities. Sine of 2t equals 2 times sine t cosine t. That's one of those trig identities. So now that we know this, now we can say what sine t is, we can say what cosine t is by using the trig triangle. So in the trig triangle, the angle is t. And what do we know? We know that x over 3 equals sine t. So x over 3, opposite over hypotenuse, is sine t. And now we can solve for the third side. We know that that's just going to be, oh, let me move this.
Our original.
All right. Actually, let me just draw this over here. Okay. X over 3, and this one is the square root of 9 minus x squared. Okay? And so now we can say what cosine t is as well. So finally we get 4.5 times t plus 0.5 sine 2t. You make your substitutions and you get 4.5 times arc sine x over 3 plus 4.5 times 0.5 is 2.25 times 2 sine t cosine t is 2 times x over 3 times square root of 9 minus x squared over 3. Okay. Now, suppose that we did have boundaries we wanted to evaluate this. I actually want to check something. Is this right? In other words, what if I gave you the boundaries from 0 to 3? If the boundaries are from 0 to 3, then that should give you a quarter circle, and the area should be 1/4 pi r squared. So from evaluated from 0 to 3, we should get 2.25 pi. So is that true? Well, let's take this expression and evaluate it from 0 to 3. So on the first half, you get plug in 3. Second half, you get plug in 0, and then you subtract. So evaluate it and see what you get. A lot of things wind up knocking out to 0, and you wind up with 4.5 arc sine of 1. Well, what is arc sine of 1? The angle whose sine is 1 is 90 degrees, which is pi over 2. So 4.5 times half pi is 2.25 pi. So this lets us evaluate it from 0 to 3, but now we can actually do the integral and evaluate on any boundaries we want, because we have this new technique.